everybody, it's Mrs. Hofferberth. Let's talk about covalent bonding theory today. In a covalent bond, the atoms are actually being held together by the attraction of shared electrons to the nuclei. So if you think about this, remember we said every type of bonding is characterized by an attractive force between positive and negative charges. You have your positive nuclei, and if there are electrons between those nuclei, they can actually be attracted to both of the nuclei at the same time. And this is where this idea of having electrons being shared between two nuclei comes into play, between two atoms. The electrons are attracted to both of the atoms. And in order to have that happen, those electrons are localized between the two nuclei, between those two positively charged atoms. And when you have this attraction, you're going to lower the energy of the system. So if we take a look at what's called a potential energy diagram, where we can see how the energy, the total energy of the system, the potential energy of the system changes, depending on where those nuclei and electrons are. If the nuclei are kind of far apart, so the distance between the two nuclei is relatively large, there are indeed those electrons between the nuclei, but it's kind of too far away for them to really be interacting with each of the individual nuclei. So they tend to be more localized, interacting just with one nucleus because the other one's too far away to be attracted. As the nuclei get closer together, so maybe we're here, the electrons start being able to be attracted to both of them. This is a good stabilizing interaction, and that's going to lower the potential energy of the system. And so we see that the potential energy starts to go down. As the nuclei get closer together yet, those electrons that are between the nuclei, I'm not sure how I'm going to draw that, but there's electrons between those nuclei, are able to interact with both of the nucleuses, and they're attracted to those positive charges. And that decreases the potential energy even more. And in chemistry, lower potential energy is more stable. This is a good thing. Now, there's a kicker. If you keep trying to squish the atoms even closer together, there comes a point where the two nuclei, the protons in the two nuclei, start to actually repel one another because they get so close. So you will see if you keep pushing this, that at some point the energy starts to shoot way up over the top. And this corresponds to having your nuclei basically on top of one another. So there's a sweet spot. And that sweet spot is this lowest potential energy point along this diagram, along this curve. And this corresponds, the length that this corresponds to is the average bond length for our covalent bond, for this sharing of electrons to have the best positive negative attractions between the electrons and the both nuclei. So that's kind of the lowest potential energy. And I want to point something out, that on this potential energy diagram, not interacting is considered a 0 point of energy. So there's nothing going on. And the well of this potential energy curve is going to have a negative value. So maybe this is negative 200, and it's typically given in kilojoules or kilojoules per mole. And so your bond and your energies of your bonds, that's going to be a negative change in energy because you're releasing energy, which is stabilizing when things come together. The number of electrons you have involved in your bond will affect the bond strength and the bond length, the average bond length. So if I take a look at two different potential energy diagrams here, we can see that one is deeper, so it has a deeper potential energy, so maybe negative 300 kilojoules per mole, whereas the other one is shallower up here, maybe at only like negative 125. That's your bond strength, how much energy it would take to rip those atoms back apart. So your bond strength is impacted by the number of electrons involved in the bond, as is the average bond length. So your average bond length is found at the distance that has the lowest potential energy. And these distances are typically given in picometers times 10 to the negative 12th meters, or in angstroms, which is times 10 to the negative 10th meters. And so, I'm going to make up some numbers here. Maybe this is 95 picometers, and maybe this is 125 picometers. If you think about it, the more electrons you have shared between the nuclei, the greater the attractions are going to be. And so having a deeper, stronger, stronger bond, shorter bond length, this is going to correspond to having more electrons in the bonding interaction. Whereas the shallower well, with its weaker bond, so lower bond strength, smaller bond strength, and a longer bond length, is going to correspond to having less electrons involved in that bonding interaction. And we see this experimentally with things like bonds between carbon. Because carbon, if you've got two carbon atoms, you can have 2 electrons shared between those 2 nuclei in what we call a single bond. We'll talk more about this in just a second. You can have 4 electrons shared between the 2 nuclei, and you can also have 6 electrons shared between those 2 different nuclei. The more electrons are involved in bonding, the stronger the bond is going to be, the deeper that well is going to be, and the shorter the bond length is going to be. Now, this number of pairs of electrons involved in bonding, that's your bond order. If we look at the bond that forms between 2 fluorine atoms, and for covalent bonding, we always talk about just 2 atoms being bonded to each other because they have to share those electrons. If we look at fluorine, there's just 2 electrons that are involved in that bonding interaction. And we can draw it as dots, but more often, electrons that are involved in bonds, we're going to draw as a line. And so this line is a pair of electrons. And so this would correspond to a bond order of 1. And we call that a single bond. If we look at a bond between 2 oxygen atoms, it turns out that there are 2 pairs of electrons being shared between those oxygen atoms. And so we typically draw that with 2 lines indicating those shared electrons. This has a bond order of 2, and we call it a double bond. This is going to be a shorter, stronger bond than a single bond would be when we have our similar atoms interacting with one another. If we take a look at the bond between 2 nitrogen atoms, it turns out there are 3 pairs of electrons that are interacting with one another. And so we typically draw this as 3 lines. This corresponds to a bond order of 3, or a triple bond. So to emphasize what's going on here, your covalent bonds that hold 2 atoms together are caused by the sharing of electrons between 2 nuclei, because the electrons between the atoms are attracted to both of the atoms at the same time. The more electrons we have involved in this sharing interaction in this bond, the shorter and stronger your bond is going to be, and the greater the bond order is going to be. Now, covalent bonds form between 2 non-metal atoms. And when we look at the properties of compounds that contain covalent bonds, we find some patterns. So first, these do not conduct electricity ever, either as solids or once they're dissolved in solution. This makes sense when you stop to think about it, because we said that in order to conduct electricity, there had to be a flow of charged particles. Because the electrons are trapped in the bonds, they can't move anywhere. There's no way for those electrons to move throughout a substance. And because this is about a sharing of electrons, you actually have a same amount of electrons and protons in the overall molecule, and so it's neutral. There's no charged particle to move. It is true that this is the time when we really truly talk about molecules. Covalent compounds are actually made up just of discrete molecules. So if you take a look at something like carbon dioxide that we exhale all the time, we draw it as CO2. And unlike a formula unit for an ionic compound, where we're really just showing the ratio of a larger crystal lattice, in this case, that's actually the atoms that are attached to one another. So each molecule contains just 1 carbon and 2 oxygens. They are individual molecules. So once we have that understanding, this explains why covalent compounds tend to melt at lower temperatures. It's relatively easy to separate the molecules from one another because there's nothing in terms of a chemical bond that holds them together. I feel like I have to put a caveat in here. We are going to talk about what are called the intermolecular forces that do allow individual molecules to stick together at lower temperatures, but you don't have chemical bonds holding those molecules together, and thus it's relatively easy to separate them. And then solubility is kind of a mixed bag. Some covalent compounds will be soluble and some will be insoluble in water. And it just depends on whether the electrons are being shared evenly or unevenly within that molecule. And we'll talk a lot more about that in our next unit.